Okay, so the last speaker today, and then there will be a coffee break, is Todd from St Andrews, who will speak on escape from entropy.
Thanks very much. Thanks for the invitation. I should reciprocate by apologising to Richard for this being the third time he's seen this talk. Hopefully this is even better than last time. Okay, so this is joint work with Godofredo Iommiand in Santiago and Anibal Velozo in Yale. I learned from Facebook today that it's Anibal's birthday today, so there we go. Okay, so let me just set up the type of problem. So in classical settings, when I say classical, I mean whatever I want it to mean. So entropy is upper semicontinuous. Okay, so really I'm going to be dealing with shifts. So classical settings would be subject to finite type. So let me say e.g., but really this is what I'm really talking about, this kind of thing. Given sigma, going from capital sigma to capital sigma, a subshift of finite type. So i.e. sigma is a subset of some finite alphabet. Sorry, sigma is a set of words, not words, sequences on a finite alphabet, and you have some kind of one-step transition rule. Okay, so if you've got that, if you've got mu, and you've got mu n, these are contained in, this is supposed to be a script m, and this is sigma invariant probability measures. Okay, so I'm just setting up notation really. So if I've got that, then if I have mu n tending to mu, then if I look at the entropy of the mu n, and I take a limit, well the limit will never exist, so I can take mu sup, that's less than or equal to the entropy of the limit measure. Okay, so I imagine this is quite familiar to a lot of people, but let me just recall the definition of some of these things to set up notation, and for anyone who's not familiar. So, recall definition. So, given Pn, the set of n cylinders. Okay, so I'm in the shift case, so these cylinders are very straightforward to write down. So i.e. cylinders like this, so x0 up to xn minus 1. So that's the set of y in sigma such that y0 is equal to x0 up to yn minus 1 is equal to xn minus 1. Okay, so this is an n cylinder. You take a collection of n cylinders, and that's your Tn. Then you can write h mu is equal to the limit as n goes to infinity, or minus y around sum c in Pn, so let's switch Pn, the measure of c log the measure of c. Well, so there's a minus, you take a minus there. Okay, so that's the definition of measure theoretic entropy. So for example, it's relatively straightforward to work out that if you've got alpha 1 minus alpha Bernoulli measure, so sigma is equal to 0, 1 to the 0, the full shift, then the entropy, so mu alpha, and the entropy of mu alpha is equal to minus alpha log alpha minus 1 minus alpha log 1 minus alpha. Okay, so you can see that actually at the first stage when n is equal to 1, you get the measure of your first cylinder. Your first cylinder is going to be like, one cylinder going to be like that. It's going to have a measure alpha, so you get alpha log alpha. And then your other cylinder there is going to be a cylinder starting with 1, and so you get 1 minus alpha log 1 minus alpha. And then if you keep on doing this, you actually get the same number all the time, except you get an n in front, but that n cancels here. So okay, so here, if you look at alpha mapping to h mu of alpha, this is continuous. Right, not oppositely continuous, but of course you can, for a given alpha greater than 0, for example alpha is equal to half, be a natural one, there exist mu n formed of sums of Dirac measures, Diracs on periodic points, such that mu n tends to mu alpha as n goes to infinity, but this guy here has entropy 0 for all n, and this guy has entropy positive. Right, so point being that entropy can jump up in the limit, but can't jump down. Okay, so that's just a quick reminder of that area. So what I want to do is I want to look at non-compact settings where things can go wrong. Does anyone want to ask any questions about notation or anything? Okay, fine. So, non-compact settings. So again, I'm going to stay in the world of shifts, which is both nice and not nice at the same time. So we were inspired to look at this kind of problem by some recent work. So recent, which I'm not going to give chapter and verse on. So recent interest in USC, upper semicontinuity, for geodesic flows. Of course, it's not the same as a shift, but that's some relation. On non-compact surfaces. And there are people in the audience who did this work and know far more about this stuff than me. So, Einsiedler, Hall, I should probably say Godofredo there, but he's not doing it, so not worry about spelling his name. And Velozo himself, more recently, and so on. So if there's anyone missing there, I apologise. But certainly there's a couple of, well, a number of papers with these authors and with Anka, with other people, addressing upper semi-continuity questions, amongst other things. Okay, so from my point of view, as someone who's not very good at geodesic flows, this is quite sophisticated stuff. So let me say sophisticated, which is definitely true. But there is a lot of structure. So for example, one thing that happens, which is going to be common for us, is going to be local compactness. So here we'll consider non-compact countable Markov shifts. So I'm going to call that CMS. So these have less structure, but I mean shifts are quite nice to deal with. So we're simplifying in some ways, and simplifying quite a lot of ways. Okay, so what I want to do is I want to give you an example to kind of lead you into the topic. This stuff applies way beyond this example, but hopefully the example gives you some idea about what's going on. Okay. So, well, and the example has an added virtue here that it's German. So, to illustrate, so I'm going to call this sigma SV. So this is some subset of the full shift. And you can explain the transition rules in a couple of different ways. So I'm an interval guy, so I like thinking about this through intervals, but actually for this talk that's not the best way to think about it. Let me give you that way of thinking about it and then move on to the other one. So, so you can't really see what's going on here, but there's infinitely many of these branches. The first two are full, the rest are not. Actually, the Markov diagram shows you more what's going on. So if I label this interval by 1, label this interval by 2, and so on. So the point is, I have a Markov diagram. So this tells me what transitions I'm allowed to make. Right? Am I allowed to go from n to k in my sequences? So from 1, this is a full branch thing, so I can go from 1 to itself, I can go from 1 to 2, I can go from 1 to 3, I can go from anywhere from 1. Similarly, this branch here is full branch, so I can go back to 1, go to itself, go as far as I like to the right. But the difference starts at 3. So from 3 I can go back to 2, but I can't go to 1. Okay, so do everywhere else. And similarly at 4 I can go back 1, and I can stay where I am, or I can go as up if I will. Okay. So this is the Markov diagram that codes that gives you the rules for the sequences in here. If you've got a sequence, you've got an x0, an x1. Well, it has to be the case that whatever the number this number has to be either to the right of it or at most one step to the left of it. Right. So the question is, can we show upper semi-continuity of entropy in this example and more generally? Okay, so the first question you might ask yourself is, well, what topology am I looking at? I haven't really mentioned that here. There I was thinking about the weak star topology, but non-compactness causes problems, right? So let me just quickly address that. So first question, what's a good topology? So, what topology to use on N? Okay, I mean, there's going to be a straightforward answer, but maybe not totally obvious why, if you haven't thought about it a bit, so let me just explain that. So, the usual generalization of the weak star topology in the non-compact cases is the vague topology. So, vague topology. And what does that say? That says that mu n converges to mu if the integral of phi d mu n converges to the integral of phi d mu for all phi in compactly supported continuous functions. So compact phi, so it's a psi such that psi going from sigma to r compactly supported.
So what's the metric on sigma?
Right, that's a good question as well. So the metric on sigma is just the usual shift metric. So yeah, you take so if two sequences agree, the symbols all agree up to the nth step, then but they disagree at the end plus first step, then the distance between those two is 2 to the minus n. So just the usual metric for shifts. But yes, that's a good question. Okay, so that's the main topology is what you would think you should do, but actually it doesn't work. And I'll slowly reveal that as I erase this thing. So somebody told me that the Austrians are even better than the Germans at this. I know that's controversial. But, I tried to learn how to do this in Austria. I realise it's not very hard. Sorry? The Swiss are. Okay. Anyway, certainly the British are not very good. You can see. Oh, I'm Irish now as well. So. Anyway, right. So the problem is, if you're not locally compact, then this set C0 is bad. So, but if C and S, is not locally compact, then C0 is actually empty. Okay, it's kind of surprising, I would say. Well, if you don't think about it for very long. Yeah, so the support of continuous functions should contain open sets, and compact sets, in this case, have no interior. So
this one is not locally compact.
Correct. So this one's not locally compact, so in this case, C0 is the empty set. So vague topology is not going to work for this particular case. Okay, so how do you say, as in sigma SG. Yeah. So for shifts, you can characterize local compactness by at each state in your Markov diagram there has to be finally there can only be finally many arrows going out. Okay, so that characterizes local compactness in this setting. So you can see here there's infinitely many arrows going out from every state, so it's not really compact. Okay, but there's a way around this. So we'll use convergence on cylinders. So that is basically what it says it is, which is to say that mu n converges on cylinders to mu if, well, for all C in an n cylinder, too many n's. Mu and C converges to mu C. Okay, so a natural way of thinking about convergence, but just worth pointing out the vagueness, very clear convergence. So my co-authors, Iommiand Velozo, have a paper which includes various facts about this topology. But one of them is that if the topological entropy of the shift is finite, and again that's true for this case here, which maybe you can't see anymore, then actually if you look at the space of sub-probability measures, so this is mu sigma invariant measure with mu of sigma less than or equal to 1. So that space is compact. Under the cylinder topology. By which I mean the topology generated by this kind of images. Okay, so that's what we're going to use, and this space is going to come up again later in some statement of the theorem.
Is the topological entity sort of a suit over, how do you define it?
Okay, I was thinking about trying to get away without defining it, but I wanted to use Godofredo entropy, which could be defined as, well, Godofredo proves that you can define it as a supremum over the entropy on the compact invariant sets. So you could think about that way, if you like. Yeah. And just to say, for this example here, that's log 4. So, definitely finite. Okay, so I'm interested in upper semi-continuity of entropy. This is my topology. So let's show you what can go wrong. Example for upper semi-continuity or otherwise. So consider the subspace sigma n of sigma SV. Okay, so I'm in here, but I'm going to take a subspace coded by, so I'm going to look at just 3 symbols, so I fix n, and then I look at 3 symbols, n plus 1, and n plus 2. Okay, so the Markov diagram that I've drawn for the whole thing, well, this has to, this is going to inherit that, right? So this means I can go from n to n plus 1 to n plus 2 to itself. This one can go one step back, this one can go everywhere as well actually. Okay, but n plus 2 can only go to n plus 1 or itself, so you could also code this by a matrix. You get 1, 1, 1, 1, 1, 1, 1, 1, 0. Right? So this corresponds to the fact that you can't go from this third symbol back to the first, or the zeroth, well, yeah, third to the first. Okay. So I look at all the sequences which just consist of these symbols using this transition, these possible transitions between those symbols. Okay. So here topological entropy is classical. So this has h top sigma n. Well, actually, you just look at the leading eigenvalue of this matrix, transition matrix, and you take log of it. Log lambda 1 for lambda 1 is equal to 3 over 2 plus square root of 5 over 2, which is approximately 2.6. I don't really care what it is exactly, but I want it to be greater than 2. Okay. I think I claimed earlier in this conference that I don't like numbers. Occasionally I use numbers. There we go. Okay, so let nu n be the measure of maximal entropy, and again this is a classical object, maximal entropy. Okay, so there's a classical way of showing that there's a measure on this subspace which has the maximum possible entropy, and the variation principle tells you the entropy of that is equal to this thing here. Okay, so in particular, the metric entropy of mu n is equal to log lambda 1. Okay, and now I want to let mu 0 be half Bernoulli measure. Bernoulli measure on the first 2 symbols. So on 1, 2. So remember, this is just a full shift, right? Because the first 2 branches were full. Okay, so what I'm going to do is I'm going to take a sum of my nu n and my nu 0 to form my measure of interest. Let me just point out that this has metric entropy equal to log 2. Okay, again, that can be thought of as classical. So then I'm going to let mu n be equal to a half times mu 0 plus a half times nu n. I'm thinking n greater than 3. Okay, and there's nothing special about a half here. I could have chosen any number between 0 and 1. A half is a standard thing to look at. So what I want to do is to, when I've gone through the mechanics of all this stuff, is to calculate the entropy of this guy and see if I can derive upper semi-continuity of entropy. Okay, so when I take the entropy of a sum of measures, that's going to be the sum of the entropies appropriately rescaled. Yeah. So let's do that shortly. So, for each n, I can compute the entropy of mu n. So that's going to be equal to a half times the entropy of mu 0 plus a half times the entropy of mu n. Okay, so, and that is equal to a half log 2 plus a half log lambda 1. Okay, and in particular, so remember this is approximately 2.6. Sorry, something wrong there. No, that's right. Okay, so in particular, this number here is greater than log 2. Okay, so I'm asking about upper semi-continuity. So the first thing to check is what does mu n converge to? Okay. So the question is upper semi-continuity, yes or no? So first let me show what this converges to. So since, well, mu n converges on cylinders, well, what does it do? So mu n is just supported on these symbols, right? On the sequences of these symbols. So as n gets bigger and bigger, then that goes off to infinity. So what happens is that for any cylinder that you pick, eventually its mass is going to go off to 0 as n goes to infinity. Okay, so that means that if you're looking at mu n, the only thing you've got left is this half mu 0. So mu n converges to half mu 0. Okay. So recall I'm interested in this set of subprobability measures, and well, it's good because this is no longer a probability measure, it's a subprobability measure. Okay, so we've lost half the mass. Okay, so that's something that can happen. Yes.
So the full space is not considered to be a cylinder, or?
No. I wouldn't consider that full space.
It's not a cylinder.
No.
That's why you have to differ.
Yeah, sure.
Okay.
Okay, so you lost half the mass. So also, if I look at the, I'm going to call this mu infinity. So also, the entropy of mu infinity, so remember I said if you want to compute the entropy of a subprobability measure, basically what you do is you pump it up to being a probability measure, like this. Okay, so this is just the mass of sigma. Right, so you pump up this probability measure into being a probability measure, then you've got a formula for entropy, that's fine, and then you multiply what you've got there with the total mass, right? So that's just a half times h mu 0, and that's equal to a half log 2. Sorry, I meant to say a half. No, sorry, no. Okay, so if I'm thinking about my upper semi-continuity of entropy formula, Well, it's gone catastrophically wrong, right? So we've lost half the mass. We've actually lost more than half the entropy. Half the entropy. Right, so you might have thought, well, maybe to recover my anti-semicontinuity result, I have to, pump something up like this and recover the result somehow. But even when you lose a certain amount of mass, you can lose even more entropy. And this is what this example is supposed to be describing. So certainly, upper semicontinuity in the standard sense definitely fails. Okay. So let me say what does happen. Okay, so firstly let me define a quantity. I'm going to define it in a way that is going to make the theorem quite digestible. This is not how we came across this. We came upon this. I'll explain that later maybe. So what I'm going to do is I'm going to take I'm going to look at sequences μn which converge on cylinders to 0. Okay. So I'm taking measures which are giving basically more and more of their mass to infinity, and I'm looking at the entropy as that more and more of the mass going to infinity happens. So I think about this as being the entropy of infinity, right? I look at all sequences of measures which give more and more of their mass to infinity, and I look at the maximum possible entropy I can get there. Okay, so this is called the entropy at infinity. So that allowed me to say the first theorem. So it applies to this example, but it applies more generally. So let me just put some slightly more general statement. So let sigma sigma be a transitive countable Markov shift. So meaning I can get from any symbol to any other symbol. I might have to wait a long time, but it will eventually happen. With finite topological entropy. That's a necessary condition for the statement to make sense. If you have infinite topological entropy, then it's kind of obvious statement you can make. So if μn converges on cylinders to mu, then the formula is limsup n h mu n, so that's the same. This is less than or equal to the total mass of mu. And of course, if mu is equal to 0, then I put 0 here, and this term here should be thought of being 0 as well. Doesn't really matter because that's going to be 0. And then 1 minus the total mass of mu times the entropy infinity. Okay, so my hope was that the example that I gave you would motivate why you would expect to have this residual term here. You can lose some mass, and you might lose small amount of mass, you might lose a lot of mass, but the total quantity you should be interested in is that mass multiplied by the maximum possible amount of entropy at infinity. Okay, so that's the main theorem. Let me make a couple of remarks, and then please think about questions. So, if the total mass is equal to 1, then this right-hand term is just 0. So, if the total mass is 1, i.e. no mass escapes. Then we get the usual. Then we get usual upper semicontinuity statement. So yeah, this is just one. Get rid of this. It's the usual statement. I want to remark that this is quite general. We proved a sort of mini version in the case where no mass escapes. In the ergodic case, in the previous paper, the same authors, also, but in ergodic case. Okay, so this handles mass escaping, mass not escaping, ergodic, non-ergodic. And then I want to point out that the theorem is sharp. But the way I've stated it sort of makes that immediate. So the theorem is sharp. So what do I mean by that? I mean, I can't improve this constant here, right? This is the best you can do. And the way it's written here, maybe that you're already convinced by that, maybe not. So for example, yeah, so the first example, so just choose mu n as in the definition of delta infinity. So what I mean is choose some mu n such that the lim-sup of entropy of mu n, so the mu n goes to 0 on cylinders, and so that the lim-sup of the entropies basically goes to delta infinity. So if you choose that, I choose a sequence which gets as close as you like to that, then the left-hand side of star, left-hand side of star is going to be approximately, well, the lim-sup of this is that, delta infinity, and the right-hand side of star is also, well, mu is going to 0, so this term is going to be 0. You're just going to have 1 times this. The right-hand side is equal to delta infinity as well. So you can't improve that term there. You could also think about this previous example here where I added this artificial subspace sigma n, and I put some measure mathematical entropy on there. Or instead you could take, again, a sequence which does this, which approaches your delta infinity, and replace your mu n with that sequence. Okay, so I'm going to inscribe that on the bottom. So in our example, replace mu n with mu n, well, mu n, as in definition of delta infinity again. So I'm going to write out what that gives you on the left-hand side and the right-hand side. Once I've erased this board, maybe in the meantime you can think about doing that for yourselves. So we came to this not using delta infinity defined like that, but defined in a topological way, and then proved a variational principle at infinity. And so hopefully I have a tiny bit of time to explain that. Because actually the proof is not really, well, it's a kind of topological proof. Lots of counting. And again, some of the steps of the proof are inspired by the previous work of, for example, Heisler and like that.
So why do you want to have infinitely many arrows on the right, going on the right? Why not just 2?
On the right.
In your example, you have infinitely many arrows going on the right. Why not just 2? And it would be locally compact.
I mean, you can do that.
You can do that.
Sure. Yeah, it's close with everything. As long as the total entropy is finite. Yeah, close with everything. Yeah, I tried to give us an extreme example. But yes, the survey
But the
works.
setup is interesting in that case too.
Yeah, it covers all the cases. So I tried to, yeah, it just has to be a transitive, totally transitive countable Markov shift. With finite entropy. So, yeah, so are there any more questions on the statement? Oh yeah, sorry, I wanted to finally finish this little bit here. So the left-hand side, if I did that, would be, what would it be? So you get approximately a half log 2, because this is the entropy of the half minute measure, plus delta infinity instead of this log number 1, and then on the right hand side of star you get half log 2 plus delta infinity, because yeah. Okay, so let me give you the topological version, and maybe that can sort of inspire you to think about how the counting might have happened.
Maybe a silly question.
Yeah.
Do we know that delta infinity is less than topological entropy?
Yeah, less than or equal to.
No, less than, strictly less than.
No, so you don't. No, so that's a
Very
very good
is
question.
empty, right?
I'm sorry?
If delta infinity is equal to the topological entropy, right, then wouldn't it be the case that kind of the left-hand side be necessarily bounded by the right-hand side?
Yeah, but that's an interesting case. Yeah, so I will hopefully have time to talk about that if I. Oh no, probably won't actually. When you have a strict inequality between topological entropy and delta infinity, you have things like a measure of maximum entropy, you have strong positive recurrence, if you know what those things are, and it's when they're equal that you don't, and then you have some kind of, you can have different types of behavior. Yeah, so it's, you get the best behavior when there's a strict inequality, yeah, and that's where you can really say things. Although you can say things when they're equal, you know that if a sequence of measures has entropy converging to the topological entropy, then that measure, a sequence of measures must vanish off to infinity. So there's two sides of it, yeah, good question. Okay, so let me probably just define what this is, and then say that it's equal to what I had before. So, define, so I'm going to define delta infinity top. Okay, so how am I going to do that? So, this is using Zn, n, q. So n is a big number, q is a big number, n is very big. So this is the number of cylinders x0 up to xn plus 1. I don't know why I'm using this. But anyway, okay, so well, that's what we do in the paper. So such that x0 and xn plus 1 are less than or equal to q, and the basically the proportion of times that you're below q is small. So I in 0 up to n plus 1, such that xi is less than or equal to q. This is bounded above by something small and plus to capital N. Okay, so I'm saying I'm looking at the cylinders whose first digit is smallish, whose last digit is smallish, but the intermediate digits, most of them are really big. They're away from Q, they're spending more time. So if you take Q really, really big, this means that most of the digits are near infinity. Right? So I'm going to set delta infinity top. Let me hopefully I get the right number of limits in here. So there's a limit for the Q, and then as n tends to infinity, thelimsup n 1 over n log Zn n q. So, coming back to the question about how I measure topological entropy, one way of doing it would be to count these number of cylinders with, say, well, the first digit being fixed at some q and the last digit being fixed at some q and not having this restriction. That would give you the Gregorian expression, the Gregorian entropy. So this is like the Gregorian entropy, but I'm also assuming that most of the time I'm away and I'm like near infinity, basically. Okay, so theorem 2. ITV is a variational principle. And that is to say that delta infinity top is equal to delta infinity. Okay, so that the topological measure of entropy at infinity is the same as a metric version of entropy at infinity. Okay, I should also mention a quantity which is the same, which is loosely defined in the paper. Okay, so let me just give you
Sorry,
yeah.
delta infinity is for a specific sequence of measures.
It's so you take a supremum of all sequences, which
Of all measures.
of all sequences of measures which go to 0 in the cylinder.
Okay, I see.
Okay, so idea of proof. So idea of proof generally. Idea of proof of theorem 1. Theorem 1 is use the Katok entropy formula. So use Katok entropy formula. So I'm lying here, but it's something like this. Look at the finite partition. This is not quite what we do, but it's more like that. The finite partition. If I look at the one cylinder starting with 1, the one cylinder starting with 2, the one cylinder all up to k, and then I look at the rest, k plus 1, union k plus 2, union da. Okay, so that's the infinite bit. And so, usual entropy formula estimates how many bowling balls I need. Bowling balls. To cover these guys. And then delta infinity estimates, well, there's a big top really, estimates how many need to recover the non-compact part to cover the rest. Okay, and that's a lie, but morally that's basically what's happening. There's quite a sort of kind of quite complicated counting arguments to try and go a transition between covering these guys and covering those guys. It's not quite those guys anyway. But I think I've basically run out of time, so thank you for your attention.
Thank you. Questions?
Your topological, oh, sorry. Wait, somebody.
No?
Okay. The topological version?
Yeah.
It's easy to define it in a version which would not involve Markov shift, right? Just topological space? Let's say?
Yeah. I mean, so for example, when I was talking about these cases of geodesic flows on surfaces, that's the kind of thing that they do there as
For
well.
example, the Liagic definition replacing Q with a compact set and looking cylinders by epsilon orbits, and would that make sense? Or?
Yeah, I guess. I mean, yeah, I imagine. I mean, so what I'm saying here is a sort of a general approach. We don't do precisely this thing, but the general approach I could see working in lots of scenarios. Yeah, those type of scenarios. Yes, that's fine.
But to have the usual formula, you need to show that there's no escape, right? Or
No, I
mass.
don't. No, I don't show this. No, it copes with escape or
The
not.
usual formula. So mu absolute value is equal to 1.
Yeah. So then,
So how does it connect to tightness?
so
Does it
if
mean that the sequence mu is tight, or
it is tight, then you
then
only
it's
have.
clear. Then it's clear.
Then it's clear, yeah.
But the converse statement, I'm asking.
If there's
If-
no escape,
if
is the sequence
Absolute
tight?
value of mu is 1.
Yes.
Does it follow that mu n is tight?
Hold on, you know this time. Don't know. Right.
I don't know
Right.
either.
No, that's right. I see. Yeah.
What is countable formula? What is countable formula?
So it's, I mean, kind of right, without writing it, it's asking how many Bowen boards you need to cover a set of measure 1 minus epsilon. So it's a way of, if you're interested in the measure theoretic entropy of something, so you're interested in measures, you just need to look at a set which has reasonable size from the point of view of the measure, and then it says, well, if you look at the number of Bowen balls to cover that set, then that gives you the entropy, the metric entropy, the entropy of that measure. Right, so it sort of combines the topological and the measure theoretic.
Yes.
I don't know if you mentioned, but did you calculate delta infinity for your example?
Yes. So if I had 10 more minutes, I would have said that. Yes. So thank you for asking the question. So actually, in this case, this comes back to the other question I was asked, that it's the same as the topological entropy as log 4. So this actually is kind of a bad example in that sense. There's no measure of maximum entropy, and you shouldn't get measure of maximum entropy in that case. So, well, yeah. Okay.
Great. Well, thank you again.